Hello, hardworking students of Relativity who made it to the last video of this series on rubber duck physics. This is Tamás Jávor. Let's see what is left for us, reaping the benefits of all the knowledge we have acquired. In the previous video, number 8, we learned how to read space-time diagrams and how worldlines and tilted axes represent motion and relativity effects. Now it's time to use these diagrams to solve real problems. We'll go step by step through the different types of space-time problems. Number 1 will be a warm-up question, then visualizing. Number 2, time dilation. Number 3, length contraction. Number 4, the relativity of simultaneity. Number 5, checking the Lorentz transformation itself. And number 6, light signals traveling between objects moving. If you want to challenge yourself, pause the video before I solve each question and think about the answer, or even sketch it yourself. Let's get started.
The first example: constructing a moving frame's axes. The yellow duck stands on a train platform, watching as the blue duck moves past in a train at 0.6 times the speed of light. The yellow duck considers itself at rest, so it draws its space-time diagram. The horizontal axis represents position, and the vertical axis represents time. This means the axes of the blue duck's frame, CT' and X' will be tilted compared to the yellow duck's frame. To build these, the CT' axis follows the blue duck's worldline. The X' axis is tilted in the opposite direction by the same angle. That angle is the arctangent of the duck's velocity over c. Pause the video and try drawing the two sets of axes yourself. The arctangent of 0.6 is an angle of about 31 degrees. This is how we visualize a moving frame. By the way, the blue duck sitting inside the moving train also considers itself at rest in its own reference frame. Viewed from its frame, the yellow duck and everything on ground moves backwards. So, in the blue duck's frame, the yellow duck's axes are tilted in the opposite directions by the same angle. But how do we actually read distances or time intervals along these tilted axes? The X' and CT' axes may be tilted, but they are also scaled differently from the stationary axes. In real physics diagrams, we would apply a scaling factor based on the Lorentz transformation to know how long one unit should be along a tilted axis. Here, we are keeping things simple. When we show coordinates like CT' equals 10 or X' equals 2.8, they have already been measured on a diagram that respects this scaling. We won't go into the math of building those scales here, but it's important to know equal-looking distances on tilted axes are not necessarily equal in value. The second example: time dilation on a space-time diagram. The blue duck's spaceship is moving at 0.8 c relative to Earth. It carries a clock that ticks once every 10 seconds in its own frame. How often does it tick from the earthbound yellow duck's perspective? Pause here and try sketching the worldline of the spaceship, marking the ticks and comparing them to Earth's vertical CT axis. We draw the Earth frame with position on the horizontal axis and CT on the vertical. The spaceship's worldline has a slope of arctangent of 0.8. Mark 2 clock ticks on the spaceship's worldline, separated by 10 light seconds following the scaling. Or it could be, of course, any interval. Now read the time interval vertically, in Earth's frame. You will see that, although on the paper or screen it looks shorter, but taking into account the different scaling, it's longer than 10. Or than your selected interval in the ship's frame. The yellow duck on Earth sees the clock tick every 16.7 seconds, just as predicted by the time dilation formula. The third example, length contraction on a spacetime diagram. A rod is 5 meters long in its own frame. If it's moving at 0.6 c, how long is it in Earth's frame? Pause the video and sketch this out. Draw the endpoints of the rod in its own frame and then read the simultaneous positions in Earth's frame. The angle of tilting the axis is, again, 31 degrees. We draw the rod as stationary in its own frame. In Earth's frame, it's moving, so the measurement of positions of its two ends must be taken simultaneously, along a horizontal line in Earth's axis. Those endpoints won't be horizontal in the rod's frame. From the diagram, the contracted length is 4 meters, matching the length contraction formula. The fourth example, relativity of simultaneity. The Blue Duck's spaceship moves at 0.5 c, and two beacons at opposite ends flash simultaneously in the ship's frame. Will Earth observers agree? In this problem, we are not investigating the further propagation of light yet. We are interested only in the relative timing of the two flashes. Pause here and sketch both flashes in the ship's frame. Then overlay Earth's tilted axis to see what changes. In the diagram of the Blue Duck's ship, the flashes are on a horizontal line. In the Yellow Duck's tilted frame, the two flashes lie at different positions along CT-, meaning they don't happen at the same time. Relativity of simultaneity met in video 7, now visualized. The fifth example, applying the Lorentz transformation on a diagram. You are making observations at a space station. A comet and an asteroid crash into each other, measured in your frame at x equals 6 meters. Fortunately not at x equals 0, because it would have hit your head hard. CT equals 8 meters. Your best friend is driving by in her brand new space vehicle at 0.6 times the speed of light. What are the x- and ct- coordinates of the event in your friend's frame? Pause the video, find the event point, and try reading off its x- and ct- values using the tilted axis. We draw the tilted ct- and x- axes for a frame moving at 0.6 times the speed of light. From the diagram, we project the event onto the tilted axis. That is, we find where lines parallel to the other axis intersect them. So, from the event, draw a line parallel to the x- axis until it meets the ct- axis. This gives ct-. Then draw a line parallel to the ct- axis until it meets the x- axis. This gives x-. We find x- equals 1.5 meters, ct- equals 5.5 meters. Notice how these values match exactly what you would get from the Lorentz transformation equations. That's, of course, not a coincidence. The tilted axes are scaled exactly so to reflect those very transformations. This shows how space-time diagrams aren't just pictures. They are tools for solving real relativity problems. The sixth example, light pulse sent in a moving spaceship. The Blue Duck is traveling inside a spaceship that moves at 0.6 times the speed of light relative to the Yellow Duck on Earth. There is a lamp at the back of the spaceship and a wall at the front, measured to be 0.3 light seconds apart in the spaceship's own frame. It's a big spaceship. At the moment the spaceship passes directly in front of the Yellow Duck, the Blue Duck flashes its lamp. This is t equals 0 in the Earth frame, and we will place the origin of our diagram at this moment. Pause here and draw the spacetime diagram in the Earth frame. The horizontal axis is x, and the vertical axis is ct. Then, since the spaceship is moving, its axes are slanted. Place the lamp and blue duck at the origin. They will move to the right along the CT-axis. Now the wall is moving forward at the same speed as the spaceship, of course, which means at rest in the spaceship frame, so its world line is a straight line, tilted just like the spaceship's time axis. And the light pulse travels forward at speed c, so it's a 45-degree diagonal line starting from the lamp. The question is, when and where does the light hit the wall in the Earth frame? Pulse and draw the world line of the wall, parallel to the spaceship's motion, starting a ship length ahead of the lamp and moving forward at the same speed. Then draw the 45-degree world line of the light pulse. You will see that the light intersects the wall's world line at some point. By reading from the Earth's axis, you can find the time and place of the event in the yellow duck's reference frame. The x-coordinate gives you the position where the light hits the wall. The ct-coordinate gives you the Earth's time when it happens. The diagram shows that the light reaches the wall at about x equals 0.6 light seconds, ct equals 0.6 light seconds. That's what the yellow duck sees. You didn't have to transform coordinates or apply a length contraction formula. Just draw and read. That's the power of space-time diagrams.
We have now seen how to use space-time diagrams to solve real problems in relativity. By simply reading from the diagrams, we can confirm time dilation, length contraction, the relativity of simultaneity, how events transform between frames, or analyze the journey of a light signal between observers moving relative to each other. If you have followed the DP Physics video series on special relativity up to this point, congratulations! You have mastered the basics of Einstein's relativity, hopefully gaining an understanding that space and time don't behave in an intuitive way as soon as we observe them from reference frames whose speeds are not negligible compared to the speed of light in vacuum, which is, against intuition, a constant in any reference frame. If you are curious about more topics in relativity, you might want to explore things like more on space-time diagrams, namely light cones, checking how two events are separated and which could cause the other, the twin paradox, the concept of rest mass and energy, or even the general theory of relativity. If you need one-on-one tutoring for IB/DP Physics, A-level or AP Physics, or also mathematics courses, I also teach online. You can find my email in the details of my channel, Rubber Duck Physics on YouTube, only if you are using a browser, not in the mobile app. Thank you for watching Rubber Duck Physics, and see you in any of the videos you pick for watching next. Goodbye.